We're good? We're filming?
Mm-hmm.
All right, everybody, we are doing 8-2. That's a variation. I got help today from cameraman Evan. Evan, say hi. All right, there we go. So this will go quickly here. The idea behind variation are there are certain natural laws that you can model. It's called modeling. You can replicate by using simple equations. Okay, so this is a linear equation. All these are direct and then a word like direct linear. This is direct square and direct cubic or cube equation. And guess what? It has to do with the exponent. We don't write the little invisible one here. We do for a square, it's 2, and we do for a cubic, it's the third degree is our exponent. So the key thing to remember is that these graphs will look a little bit different. Each graph, here's your little viewing rectangle, there's your axes. This one will be a straight line. This viewing rectangle with your axes will be half of a parabola like that, and a cubic one will look parabolic. It'll be much steeper. If we were to draw into negative land, it would go down like this, whereas a parabola goes more U-shaped. But for all of these, we're going to follow sort of the same steps to solve. Now, in a word problem like you have in your worksheet, you're going to be told what type of a variation it is. And I've got 3 examples, okay? So for the first example, we're saying you're babysitting, and in babysitting, you're paid by the hour. I don't know what the going rate is, but let's just make it a nice round $10 an hour. In that case, you'd be saying, well, the amount of money, your pay, we'll use A for the amount of money you earn, is going to be 10, I said $10 an hour times T. Pretty simple. Every hour you work, you make $10 more. If you were to graph it, it'd be a very simple graph. I think you've been doing this for a couple of years, so I'm going to kind of gloss over that and go to the 2 more difficult ones because you're maybe not so used to dealing with square variations. All right? So if you drop a stone into a flat, still pond and you let the waves ripple out in a circle, the area of that is going to be a square variation. So suppose you know that after you've dropped like a pebble in a pond, that after 2 seconds, okay, the area is equal to 10 square meters, okay? What you want to do now is to follow the steps to write an equation that will model this square variation and then make a prediction as to what the area is going to be after, say, 5 seconds, okay? Actually, let's make it 4 seconds, all right? 4 seconds. What's the area, all right? Okay, so you might think, well, you're going from 2 seconds to 4 seconds. The area is 10 square meters. It's probably going to be 20 square meters. But it doesn't work like that when the variation has an exponent. So what we do is we determine the type of variation, and like I said, you'll be told that usually in a word problem. So we know that it's a square variation, so you write that equation, y equals kx squared. And now, so you've written the equation, then you sub in your data point. This is our one data point. So 2 seconds, and actually sometimes it's very useful to replace the letters with what they should stand for, okay? So I could replace the y with A for area. I could replace the x for time. But you know, that makes it a little bit simpler, but it's not essential. But what I'm going to do is I'm going to put the 2 in place of the t. Don't forget this exponent. K does not change, that's what we're looking for, but the area is 10 square meters. Don't worry about this m squared, that's just our unit of measurement. When you're talking about area, you know it's going to be square units, square feet, square meters, square miles, whatever. Now we're going to solve this. Well, 2 squared is 4, so 10 is equal to k times 4. I divide both sides by 4. And I get 2.5 equals k. This is called my constant of variation, all right? These are always called the constant of variation. Okay, so you hear that term used a lot. Well, once you have k, sub in your data, solve for k, sub k back in. So I go back into my original equation. I'll put it here for a second. I'll say it's 2.5, all right? And now, I want to know, after 4 seconds, what's my area going to be? Well, now I can plug 4 in right here. 4 squared is 16. 16 times 2.5 is 40. And so it turns out that the area has gone from in 2 seconds at 10 to 4 seconds, it's 40 square meters. Okay? So that would be your solution. So you sub K back in, and then you answer the question or make a prediction about something that's going to happen in the future. All right? So one more example. Here's one where I'll give you the data, and you can pause and try it on your own, and then quick check and see if you are correct. All right? Wind power is known to be a cubic variation. Wind can get more strong, and the amount of power you generate goes up by a cubic variation. So we'll say that a 5 mile per hour wind will produce 300 kilowatts. Okay, so it's a smallish generator. 5 mile per hour wind is producing 300 kilowatts, and you're told in the word problem that's a cubic variation. So again, what do? Determine the type. Well, that's easy. I've told you. Write the equation. All right, so there it is. We'll say that the power in watts is determined by the wind speed. We'll use S for speed. Okay. And now we put in our data point. So this is K we're solving for. The speed is 5. That's 5 to the third power is equal to 300. Okay, 5 times 5 times 5, 15. Or sorry, 25 times 5 is 125. K is equal to 300. So I divide both sides by 125. 125. And this is my K constant. Okay. So you can put that into a calculator and do the math. It's going to be a little bit more than 2, a little less than 3. But I'm just going to leave it like that as a fraction. There's no problem with doing that. And then I go back in and I write my equation here with K being replaced. So the power I get is going to come from 300 divided by 125 is my constant of variation. And now I'm going to plug in, oops, I didn't say what the wind speed. My prediction is, let's make a different wind speed. Let's say only 8 miles per hour. So if this goes up to 8 miles per hour, what will the power be? Okay. Well, again, 5 doubling to 10 might make you think that, oh, it's going to be less than 600. But be careful, because the cubic variation, you get a lot more power from a little increase in wind. So I'm going to take that 8 and I'm going to raise it to the third power, and then I'm going to multiply it by 5. Multiply it by my constant, rather. So 8 times 8 is 64. 250, 512. 8 to the third is 512. So it's going to be 300 over 125 times 512. And that's going to give you P. All right? So take a calculator, crunch those numbers, and you'll be surprised that it is a lot more than doubling 300, even though the miles per hour has not nearly doubled. Okay, that's how you do these. Thanks a lot.